Hi, all, and welcome to part 4 of water. We have been spending a lot of time talking about the hydrogen bonding between two water molecules, and now I want to introduce something that water molecules do when they are hydrogen bonded to one another that we hadn't yet talked about. So it's that a hydrogen atom that is in a hydrogen bond between two water molecules, right? It can shift. The hydrogen atom itself can shift from one water molecule to the other. Now, when this hydrogen atom leaves one water molecule to join the other, it actually leaves its electron behind. So therefore, it's transferred as what we call a proton. And the other name for this is a hydrogen ion. And then if we want to symbolize it, we do a hydrogen, the H for the hydrogen, with a plus. So this is a cation. It is a positively charged ion, and it is a hydrogen. Now, why do we call it a proton? That seems unusual. I brought back this little diagram from chapter 2, where it shows the makeup of the hydrogen atom. And the hydrogen atom, very simple, right? Here's the atomic number. And if you remember, the atomic number is the number of protons that are in its nucleus. So the atomic number tells you that there's one proton on here. If you remember correctly, right, that this one has no neutron, right? Deuterium has a neutron and tritium has 2 neutrons, but this hydrogen atom has none. So it is basically just a proton with an electron circling it, right? Not orbiting, but going around like this in an electron cloud, right? That electron is found in the first shell, if you remember all that. So an electrically neutral hydrogen atom is simply a proton and an electron that is circling all around it. So if a hydrogen atom transfers and leaves behind its electron, symbolized by this little circle here, then it simply is a proton, right? That's the only subatomic particle that it has that we concern ourselves with. So this is what we refer to then as a proton, an H plus, right? Because it no longer has its negatively charged electron, and so it has an unmatched positive charge. So it's a hydrogen ion or a proton. Okay, so the hydrogen atom leaves as a hydrogen ion or a proton, and the molecule that lost that proton, right, has an extra electron, and it's now known as a hydroxide ion. This is also an ion because it carries a charge. It's a negatively charged ion. I'll show you in the next thing, in the next slide. So the molecule with the extra proton, right, who picks up the proton is a hydronium ion, and that's represented as H plus. So the molecule that lost the proton is now an OH minus here because it kept the electron and lost the proton. And the molecule that picked up that extra positive charge in the form of a proton is an H3O plus, though it's often represented this way. Let me show you. Okay, so here's what I've described. The dotted orange line here is the hydrogen bond between the two water molecules, as you can see, and then I've circled the hydrogen atom that's going to jump from one to the other, but not as a hydrogen atom, but a hydrogen ion. Okay, and so then when it jumps this, let me get my draw tool. So this particular water molecule, let me circle it, becomes the hydronium ion, right? It picks up a proton, and so it has a positive charge because it gets the hydrogen ion. So now it's called the hydronium ion. And the hydroxide ion, this is what is this part, right? It gets the electron from the hydrogen, and so now it is a hydroxide ion. It looks like this, right? And so often this is not, most of the time it isn't shown to you in structural form. You can see two water molecules, that's referring to both of these, and then they can become, when this proton exchange happens, the hydronium ion, H3O plus, right? 1, 2, 3 hydrogens, that's the H3 there, and the oxygen, right? It has an overall positive charge, plus the hydroxide ion, which you can see like this. Sometimes this is simplified even further and just shown to you as water molecule, one water molecule splitting into H plus and OH minus. However, this is a simplified version, and this is not how the protons exist. They don't exist free like this. They do attach themselves to another water molecule and make a hydronium ion. So even though this is a simplification, but that's not Correct. That's not how it exists. Okay, now from having taken chemistry, I'm sure you know, but I just remind you that when you have an arrow, right, that goes in both directions, it lets you know that this is a reversible reaction, which means that two water molecules can exchange a hydrogen atom and become this, and these can go, right, this hydroxide ion can pick back up a proton and you can go in the other direction, right? So you can go in both directions. So this is not something that happens to every water molecule. They say it's statistically rare, but there are so many water molecules participating in liquid water that overall you do get concentrations of these ions that are meaningful to life. So pure water, right, which is just made up of water ions, has a steady state concentration of hydrogen ions and hydroxyl ions. So it's basically saying this: hydrogen ions, because you could say hydronium ions and hydroxyl ions, and both of these are found at 10 to the negative 7 molar, right? And if you want to find out what that is, the molar, you can look at the end of the chapter. I'll remind you in case you don't remember. I have a slide that helps you with that. And so the steady state concentration lets you know that it's going back and forth, right? And at the rate where the reaction goes from, water molecules over to these ions, matches the rate at which, that's the steady state, so you don't change the concentration, matches the rate at which the two ions get together to make the two hydrogens. So the forward, if you want to call this the forward, matches the reverse. And at that point where we have this steady state, it's a dynamic equilibrium. So equilibrium is not that things have stopped, right? When reactions stop, that's actually not a good thing for life. An equilibrium just tells you that the relative concentrations, whatever they are on either side of these arrows, stays constant. But it doesn't tell you that it doesn't happen anymore. It just means for every one that goes from left to right, one reaction goes from right back to left. Okay, so at this steady state, these ion concentrations are found at 10 to the negative 7. They have to equal one another, right? Because you don't get, if you're in pure water, you don't get hydroxide ion without a hydronium ion, right? Because they're coming from the same process. And so they have an equal concentration, this to this in pure water, because they only come about at the same time. All right, so if we want to look at it with nice little space filling models, here's what it looks like here. Here's our hydrogen bond between the two water molecules, and then the loss of this hydrogen atom as a proton over to this water molecule, and you make the hydronium ion, H3O+, and you make the hydroxide ion. Right? So here's another definition for this. It's concentration of, obviously the H plus and the OH, but H plus represented as this are equal in pure water. And it's a state of dynamic equilibrium in which water molecules dissociate at the same rate. So the dissociation is going this way, right? That's the dissociation at the same rate at which they're being reformed, right? Like that. Okay, so that's the double. Sometimes you see an arrow, a double-headed arrow looks like this as well, just in case. So I just don't want you to be wondering what that is if you see that. So you can see somehow I'm on an angle now. You can see that's the equivalent, right? These two are the same. Sorry. These two are the same. A double-headed arrow, that's an equal sign. That's nice. Look at that parallel lines. The double-headed arrow is the equivalent of this. It's just telling you that the reaction is reversible. Okay, so let's define acids and bases in a biological term. So any substance that releases hydrogen ions, the protons, right, into solution are called acids, right? So here's hydrochloric acid, right? Makes and releases, right, when it dissociates H plus, the protons, and chloride ions like this. Now you see this as a single arrow, which tells you that it is basically not reversible, right? It really just goes in one direction. You don't see these two coming together and making hydrochloric acid once they're in water, for instance. Here's another acid, right? And we're going to meet this a lot, carboxylic acid group. R just stands for remainder or rest of the molecule. It's not the part of the molecule that we're focusing on for the example, so you'll see R a lot. We're going to see it when we meet side groups of polypeptides, side groups of amino acids, which are the building blocks of polypeptides. They want to focus sometimes on the backbone of the polypeptide, and then they'll show you the rest of the molecule as just an R. But so we're discussing things that release protons into solution called acids. So we show you the other molecules here because they are important, the other atoms. And so basically the electron cloud, is pulled away from this hydrogen atom here. So it's nice and partially positively charged. The electron cloud is right up around these molecules. Okay, much more electronegative, these O's. And so this is easy basically for this acid group to give off this proton. And what you have after it gives off the proton is the proton and then what it was left behind, right? So it leaves its electron back on the electronegative part that was pulling it anyway, that really had the lion's share of the electron cloud that it was sharing. And so you get a proton and you get the full electron left behind. And you can see now these two means that it dissociates in this way, and then it goes back. So it's a reversible reaction. I'll come back to this in a second, but I just want to show you this, right? So we already defined an acid as something that increases the proton concentration of a solution, right? And I'll come back to the base. A strong acid and a strong base, right, disassociate completely in water, right? So that's this. They disassociate completely. So we would refer to hydrochloric acid as a strong acid. And then weak acids, also bases, right? They reversibly release and accept hydrogen ions, right? So it shifts the balance of these, as I'll tell you, but this would be what we refer to as a weaker acid because it can donate the proton, but then this corresponding base of the weak acid can accept this proton back and it can go back to being an acid. Right, so this is a weak acid. In this example, what you see here, carboxylic acid. Hydrochloric acid is a strong acid. It just completely disassociates. Okay, so the acidity of a solution is defined by the concentration of the protons in it, right? So the more protons, the more acidic the solution is. Right? So the higher the concentration of protons, the more acidic the solution. All right, now we have defined what acids are. Let's define what bases are. And bases are substances that actually lower the concentration of proton ions in solution. So they reduce the number of protons or H plus ions in solution. And they can do it directly by the base can pick up the proton itself, right? So here's ammonia picking up a proton, an ammonium ion here. Or it could be, and I'll show you another example, they can pick up the proton or reduce the concentration of the proton indirectly. And that could be because they release an OH minus, right? And that OH minus binds the H plus, making water. I'm sure you can see that now. So it's not that the proton binds directly to that particular type of base, but overall we define the base as something that reduces the number of proton ions in solution. So something that dissociates and can release an OH minus will reduce the number of protons in solution because that OH minus will bind to the H plus. Okay, so an acid, again, this is a review of what we just talked about. An acid is a substance that increases proton concentration of a solution. A base is a substance that reduces proton concentration of a solution. Strong acids and strong bases, they disassociate completely. So it's going to be a single arrow basically going in one direction, and that is in the direction of dissociation, right? But anything that is weaker, right, reversibly release and accept hydrogen ions, right? And I'll show you an important one to our maintaining our own blood chemistry. And weak acids and their conjugate bases serve as buffers for us. So they serve as a way to keep the concentration of protons in our blood at a certain set point so that we don't die. the perfect way of saying it. Okay, so how can we express a range of proton concentrations, right? And this is where chemists came up with the pH scale. And the pH scale describes whether a solution is acidic or basic, right? And I took this quote from your book. It's a simple numerical method for expressing a range of proton concentrations, right? And it's a compressed range. So it makes it easier for us to understand. So let's take a look, right? In any aqueous solution, right, any water-based solution, right, at 25 degrees Celsius, right, the product of H plus and OH, right, so each one is steady state at 10 to the negative 7. Where did we see that? Here. Both of them are found at 10 to the negative 7 molar, right? That's what you see there. So in any aqueous solution, any pure aqueous solution at 25 degrees, if you multiply the concentration of the protons and the concentration of the hydroxyl ions, you get 10 to the negative 14, right? So we know this number. It's a steady state number. If we want to look, the pH scale tells us about the proton concentration, then we're just going to be focusing basically on the proton concentration, but then we can infer what the hydroxyl ion concentration is because you don't have one without the other. Why? Right? Because they come together, right? If you're in water, the only way that you generated this hydronium ion is because you generated hydroxide ion. Okay, so this is an obnoxious number. Like, who wants to deal with 1 times 10 to the negative 7? It's such a small number, right? It's 1 to the 10 millionth. It's cumbersome, right? So chemists prefer, right, to express the concentration of hydrogen ions, so we can talk about whether something is acidic or basic, right, in a logarithmic notation. And so that's what the pH scale is, right? Again, it is a numerical method for expressing a range of proton concentrations. So we can express whether a solution is basic or whether a solution is acidic. I'll tell you what those mean in a moment in terms of the concentrations of these two ions. They like to do it on a logarithmic scale, so it becomes easier, right? So the pH of a solution is equal to the negative log to the base 10 of the proton concentration. And when you put something in brackets, as we've mentioned, that means the concentration of the protons. So if I look at the pH of pure water, 25 degrees Celsius, then it's negative log to the concentration 10 to the negative 7, because that's what the concentration of protons are in pure water at this temperature. And so negative log of 10 to the negative 7 equals 7, right? And so that's right here. And so that is the number 7, which is neutral. This is at a neutral pH, pure water. That is what we consider neutral. So the concentration of protons equals the concentration excuse me, of these ions, the hydroxide ions right here, OH negative, right? They're equal because you don't get one in pure water without getting the other. And remember, this H plus is expressing basically the hydronium ion. So this is neutral. I remind you that acids donate protons into aqueous solution and bases donate OHs that will then bind H plus, or they accept H plus directly in aqueous solution. Fine. So if you have acid donating H plus, then what's going to happen is you're going to take this number off of neutral. The H plus is going to be there in higher concentration than the OH minus, and that's what you see here. Here's where the concentration of protons is greater than the concentration of OH minus. And so this is what we call an acidic solution. Okay, my timer is about to go off, but I just have a few more slides, so I'd just like to finish so you don't have to log into a whole new one. So anything that has more protons than OH minuses is considered an acidic solution, right? And it's going to have a pH that is lower than 7. And I'm going to show you another pH scale. I just wanted to sort of introduce it here. If you have bases donating OH, right, or accepting H plus, then you go into the basic range of the pH scale where the concentration of protons is less than the concentration of OH minus, and the pH number increases from 7. So from 7 to 14 is basic. These are basic solutions, and from 7 down to 0 are acidic solutions. Let's take a look. Okay, so here is a pH scale. It looks incredibly complicated, but that's only because they gave us examples of things that have the pH numbers that we are talking about. So let's take a look. Here's neutral. Again, neutral is H, where the concentration of protons equals the concentration of OH. So they put a little beaker down, and to drive it home, they gave you 5, right, protons and 5 OH minuses, right? And so each one of these ions exists at that concentration, 10 to the negative 7, 7. That's pure water. I put it in green here. Okay. In a basic solution, right, your proton concentration is less than 10 to the negative 7. So now they tried to show you more OH minuses than H plus in this solution. So it's basic. And you can see that you have the numbers increasing the pH. So a pH of 10 is a basic solution, right? That's a basic solution, and it's got, you know, more OH minuses than H plus in solution. And then if we're looking at acidic solution, this is where the concentration of protons is greater than 10 to the negative 7. It's greater than concentration of protons greater than OH minus, right? And these are a whole series of things that are acidic and about the level of acidity, right? So our stomachs, which have gastric juice, hydrochloric acid, we make hydrochloric acid in our stomachs, right? We have a pH of about 2, right? So that activates certain catalysts known as enzymes that can start to digest certain foods, and it kills a bunch of potential pathogens that don't do well at acidic conditions. So we like to acidify certain things. And you can see a lot of things that we drink, well, not battery acid, but black coffee and tomato juice and beer and vinegar, all those types of things are acidic. Urine, this shouldn't sit at 6 because your urine pH can change based on your diet. So I just threw here, most biological fluids have pH ranges in the range of 6 to 8. So they hover around the neutral pH of 7, going 6 to 8, of course, except for gastric juice, and there's certain other little compartments we have in our cells that are more acidic. They point out here the internal pH of most living cells is close to 7. What's important, though, is that between every pH number is an order of 10. So in other words, 9 is not twice as basic as 7. It's 100 times, right? And if we go in the opposite direction, you know, black coffee at 5 is 100 times more acidic than neutral, right? And tomato juice is 10 times more acidic than black coffee. So with every change in a number, we are, because we're dealing with logarithmic numbers, right? You are 10 times greater acidity as we go in that direction between every number. So, you know, if you're looking at black coffee at 5, this is 10 times at 4. This is 100 times vinegar. The gastric juice is 1,000 times more acidic than black coffee at 5 is. Okay, so this sort of tries to put it all together. And remember what the pH scale is doing, right? It's describing whether a solution is acidic or basic, and it is a simple numerical method for expressing range of concentrations. Okay, I'm getting to the end. All right, so I promised you and told you that we have to, back here for a second, we have to maintain a very tight range of pH. We cannot wildly go around here because biological processes depend on pH being stable, and you cannot go from 7 to 8 in the blood. That's alkalosis and you're gone, right? And you cannot go, your blood can't go from 7 to 6, that's acidosis, and that's terrible for us, right? So we pretty much are in the range of about 7.35. So it's about that. Our own blood is somewhere around there. We do not go very off this set point. So how do we avoid changing things? And how we avoid changing things is by using buffers, right? And so buffers, you probably know it because we use it in common language, like, oh, that person serves as a buffer between me and that other person, right? So if you have a friend that is you like for certain things and they're very irritating in other ways, and yet you have a third, second friend who can completely neutralize, we often say it like this, neutralize the annoying nature of your second friend, then they serve as a buffer between you and them. They serve to calm things down basically and keep things neutral. So buffers are substances that minimize changes in the concentration of H plus and OH in a solution. Most buffers contain a weak acid and its corresponding base. So these things can combine reversibly with hydrogen ions. Let me draw this. So we have, this is the weak acid, H2CO3. Right, and then this is carbonic acid. And this is what it dissociates into. HCO3 minus plus a proton. Right, and this is known as bicarbonate ion, bicarbonate. Oh. And this is carbonic acid. Oh, that C started off very poorly. Oh, this is going really bad. Hold on. I probably should have typed this. Sorry. Carbonic. I got to take some classes with writing with your mouse. Carbonic acid. There we go. Okay, so this is the weak acid and its conjugate base. This is what you see, or corresponding base. And then the two arrows are telling you that they can go back and forth. So if you were to increase acid, let's say, then which way would you go, right? If you increase acid, which way are you going to go, right? You have to think about that. And if you increase a base, which way are you going to go, right? So you can think about it and come back. Let me show you this. Okay, so here is the buffer resisting change in pH. So you can see it's showing you a range, right? A buffering range in which the weak base usually and the weak acid and its corresponding base operate. So if you look here, on the x-axis is the amount of base that's added in units, right? And here's the pH scale. So if you start out at this acidic pH of 2, let's say, and you add just a little bit of base, notice how the pH drastically changes, right? The number goes up because the solution is becoming more basic because you added base, right? So for just a little bit of base added, you get a big broad change in pH. You go from basically 2 to 4. Then over this incredible range, look at how much base you add, right? If you start somewhere around right here, right, you add all of this base units, and between right here and right here, the pH change, okay, it still changes, right, from 3 to 6, right? So it still changes, but, or from 4, let's say from 4 to 6, from here to here. So we still changed 100 times, right? Because this is 10 times 10, that's 100 times. But look at how much base got added in order for that. So whereas we changed 100 times just by adding 1/2 x of base at the beginning when we were outside the buffering range, right? So when you get in the middle of a buffering range at which the acid and base work, then for a lot of base added or a lot of acid added, you do not have such a change in pH, right? So it says buffers resist change by accepting or donating protons depending on what is necessary, And the reason that this is important is if we change the concentrations of protons and OH minus is we drastically affect the chemistry of the cell because we're going to change ionic bonds, for instance. And if ionic bonds are holding together our macromolecules, that's problematic, right? Because if you change whether something is an ion, then you will reduce that there would be an ionic bond and then something can unravel. Okay, so this is, I promised you that I would show you just the two things. My description of moles, right? So you can stop the slide and read, and your book's description of moles. right? And that's it. So we came to the end of water, which is great. And I will see you for the next bit.